we should gather a collection of input objects and their corresponding labels categories, usually from human evaluations to assure the accuracy of the labeling process. Okay, so they're just saying that, like from the previous example of predicting the housing price of a house based on its size, the size of a garden and the number of rooms, you're just going to get different houses of already known prices. Of course, you already know the size, you know the size, you know the number of rooms, you know the size of the gardens, and you know the price. So you're trying to get those labels, those categories, and they are from human evaluation. So that means you're training the model on already known data. Okay, then they go into the step of input pipeline. It is critical to determine the data feature representation of the machine input. Despite amazing deep learning performance regarding on-the-fly data feature learning, it is still imperative to put special attention on how data is represented to the machine. As for now, the machine learning algorithm's precision strongly depends on the input representation. Typically, we transform the data into feature vectors. Debates continue following regarding the feature step size. As a rule of thumb, we should avoid an input feature space that is too large due to the curse of dimensionality. However, it should be enough information necessary for predictive analysis. So here, I don't think this is necessarily a step, but they're just trying to teach us that, and I think this has been really automated, the way you represent your data, the input data that is going to be used in the model. But yeah, you should be aware of it, like, okay, you have this data, it looks like this. But it has to be transformed. The data has to be represented, the way the data is represented to the machine, okay, like to the model is a different way. I wouldn't spend too much time on this because right now I think these processes have been streamlined. They're not that serial. Yeah, so then, okay, now this is a real step, algorithm selection. Algorithm selection refers to identifying the appropriate algorithm which leads to highest accuracy. It is neither a trivial task nor any special process or secret source is currently available to find and pick the best algorithm. It needs exhaustive search and experience. Okay, so there are several algorithms that we're going to see below. But like I had said earlier, what is the best algorithm? What algorithm is best suited for your use case? That process is no trivial process, it's no trivial task. It actually has to have a lot of work. We say, okay, we're going to try this, it's performing this much on our data, we're going to try another algorithm, it is performing this much on our data, you know, something like that. Then from algorithm selection, then we go to training and evaluation. You'll see that this process that we've just been is a repetition of what we had already talked about earlier. Okay, so training and evaluation. After algorithm selection and satisfactory preliminary testing, the classifier or the regressor or the model is available for regular employment. The classifier's evaluation is usually based on the prediction accuracy. There are different procedures to calculate the classifier's efficiency. The most popular approach is to select a large portion of the data, 2/3 for training, and the remaining for measuring performance. Okay. In another method, identified as cross-validation, we split the training set into mutually exclusive subsets of equal size. For each subgroup, we train the classifier and the combination, and on the combination of all the other subgroups and perform evaluation of a specific subgroup. Finally, we report the average classification across all subsets. Okay, so I'm not going to delve deep. There's a lot of content here, but the point is, after selecting your algorithm, we are going to train. We're going to train that model, and then using the training data, and then we're also going to leave. Actually, what they say is that you select a large portion of the data, usually 2/3, and you use that to train. And then the other third, you use it to test. Just generally, how is your model performing? And then they also introduce the concept of cross-validation. I am not going to introduce it here, but it is a way of just measuring the performance of your model. All right, so this is just the process. Okay, you have a problem and you have the data. Okay, so of course you understand your problem and then you're trying to understand how the data will solve your problem. So you start by doing this process of pre-processing your data, trying to analyze it, looking for outliers, cleaning, things like nulls, things like extreme values. All this happens here. Then you try and look for an algorithm that best suits your data, that best suits your use case. Okay. And then after finding an algorithm that best suits your data, you're going to train your data, usually on the larger amount of your data. This one just said like 2/3. And then after doing the training, we're going to evaluate the performance of your model using the other third, the testing data. If it is satisfactory, we can use the data in a deployed system. Like we said, the whole point is to develop like a machine learning system that will help you in everyday work. Or if it's not satisfactory, you redesign, and you can redesign at any of these steps. Okay, so this is really a nice diagram to show you the process that you're going to be going through. Okay, so now let's go into the different categories. So supervised learning divides into two general categories: regression and classification. So for regression, in statistics, regression consists of statistical analysis for determining correlations between variables. It includes different methods for modeling and examining various variables with the primary goal of exploring the relationship between dependent and independent variables. Between the dependent and independent variables. So these are other keywords that have been introduced: dependent and independent variables. So you see that the dependent is what we've been referring to as the label, is what we've been referring to as the output. Then the independent variables are the ones we've been referring to as the features or the input. More particularly, regression analysis clarifies how the typical value of the dependent variable changes when the associated independent variables are varied. Experts utilize regression analysis for prediction in which there is a substantial overlap between statistics and machine learning. Okay, so this is just like a statistical introduction to what really regression is, and it's a statistical method for analyzing or determining the correlations between variables. Basically, that is it. It's going to get simpler. But before we had seen regression, you use regression when your output, what you're trying to predict, is a continuous variable, like is numeric, in short. So regression analysis includes parametric and nonparametric methods. In the parametric approach, the regression function defined in terms of measurable number of unknown parameters that will be estimated based on the data. Linear regression is the most popular parametric regression method. Non-parametric regression points to techniques that form the regression functions as a set of functions which may be infinite dimensional. There are also different other types of regression models like polynomial regression, ridge regression, lasso regression, which is beyond the scope of this article. So also, I'm not going to delve deep into what regression, the different really kinds of regression. I'm going to look at the popular ones, but here they're just trying to introduce you to the concept of the parametric and non-parametric methods. Okay. So for parametric, you know the number in terms of measurable number of unknown parameters, okay, that will be used to estimate the data. So for parametric, you know the number of parameters you're going to use. For non-parametric, you don't know the actual number or you don't even know the parameters that you're going to be using. Okay, so you can delve deep into what parametric and non-parametric is, but that's just a basic introduction. Okay, so the most popular kind of regression, as a refresher, we saw that regression is the one we're going to be using when we want to predict a continuous variable or a numerical variable. So linear regression is what you're going to see that is the most popular, and I think it's the simplest models, and it is usually advised to go with the simplest models for a start, and you see how they perform, and then you can eventually go on to the more complex ones. So linear regression, what is it? It is a statistical approach to predict the value of a quantitative variable. Quantitative variable is really a numeric variable, okay? Based upon an assemblage of independent variables, we attempt to determine the quantity of the dependent variable, which is the outcome of the functional operation of the independent variable. So this is just complex, using a bit of complex language, which is unnecessary really. But in short, you're just you have different independent variables, like we saw, we're going to be referring to them as a feature, and then you want to use those to determine the quantity of a dependent variable. So it's quantitative, numerical, and it's the dependent variable is just the outcome that we're talking about, the outcome, the output of the model. So a linear regression points to a particular regression model that is entirely based on linear operations. Starting with an easy case, a single variable linear regression is a technique for modeling the connection between a single input variable and an output dependent variable using a linear function, just a line. So we're going to see, this is the simplest linear regression example, okay? So what it is really is just, for example, in this case, you're just trying to build a technique for modeling the connection. So you're just trying to see what is the connection between a single input variable, okay, and an output variable. So what is the connection between this y and this x? Okay, so you have different examples of that, and you want to build a connection between this y and this x, just like we learned in school. Using the different data points, you try and get a line that best fits. You draw out a line that best fits. And that line, the y is equal to mx plus c, is your linear regression function. It's really as basic as that. So we show a visualization representation of a linear regression below. All right, so a linear regression model fits a line to the data. Like I just said, you plot your data, you're like, okay, for this particular, we have x and y examples where you have like the x is like maybe 2 here, and then its corresponding y is like 2. So you plot this data point, then you continue that process. You have an x that is 5, and those are the independent variables, and they are known dependent outcomes. Okay, so you plot a line, and then that line is the line that best fits the data. And that is the model really. That is the line. So a linear regression model fits a line to the data. The difference between the prediction and the actual value determines the loss. So you're going to plot this line, and you see the line that best fits, because you're going to be using this line to predict. Okay, so for example, if you come here, maybe this is a 5, they didn't put the axes, and then you say, okay, for a 5, what is my model going to predict? You see it is going to predict something like maybe, I don't know, 5.5, but in actual sense, the actual value for a 5 is like maybe a 4.9. So the difference between this prediction and this actual value is what we're going to be calling the loss, okay? So multivariable linear regression, multivariable is just many variables. Here we are just looking at single variable, and this is the notation. So it will be y is equal to ax plus c. So you can see that the variable here, the independent variable is x, and then the dependent variable is y. And then you build up, this is the line that has been built that best suits this data that you've given it, okay? So multivariable linear regression is a more general case where the model represents the relationship among multiple independent input variables and the associated output variable, that's the dependent. In this case, the output is a linear combination